And we're talking about a position function. So where something is, how far away it is in relation to time. Maybe it's always moving further away. Maybe it moves further away and comes back. I don't know. That's what we have to figure out given some things here. So the first thing that we want to do is let's interpret the following. Let's interpret S of 2 equals 4. Any idea what this represents here? Well, first of all, we can see that T is 2, right? Our time was replaced by 2, and our output is 4. So some annotations to myself, if I were to put this in here, I know that this is my time. And my output, S of T, S is going to be my meters. Right? So I've got time in seconds, and then I've got meters, my distance, my position. So what does that tell me about this particle? At or after how much time? Leilani? How much time has gone by according to this? At or after how much time? 2 seconds. September, what do I know about this particle? A particle's position is modeled by S of T. So I'm talking about this particle here, this thing, whatever this thing would be. I'm calling it a particle. It could be a car, it could be a ball, whatever. Something is moving, right? At a time of 2, what do I know about it? Go ahead, Leilani. It's 4 meters away. Oh, classic. Classic, you just forgot, just slipped your mind, huh? Okay, nothing there, all right? We're not talking about increasing, decreasing, any kind of rate of change here, because this was a position function. Now what we talked about yesterday is what if we take the derivative of that? What if we take the derivative of something? Let's say I take S prime of 2, and let's say S prime of 2, the derivative at 2, is negative 3. This is much different. Now we can still start this the same way. We still are given the time at or after 2 seconds. I'm using the same X value for each of these, or T value. Except this time, we know something different about the particle. Cariana, what do I know this time? The particle is what?
It's decreasing.
It's decreasing. Its position is decreasing. Now, before I even go on from here, what does it mean when I have a change in position over time? Change in distance over time. Let's go science, folks. What does it mean when I have a change in distance over time? Say that again, Leilani. Velocity. So if I'm talking about a change in position, the rate of change of my position, the rate of change of my distance, I'm going to be talking about velocity. So after 2 seconds, the particle's velocity, so I don't have to say its distance is increasing or decreasing. I could just say the particle's velocity is negative 3. And of course, we're talking about velocity, so I'm going to say meters per second. I'm going to give that rate. So we're going to specify a little bit more today. Instead of saying something is increasing or decreasing and by how much, I'm just going to stamp it with velocity. Notice my units here. All right, what else can I do here? Let's say I found the second derivative. This is going to blow some brains up a little bit, but stay with me. What's the rate of change of velocity? What do we call something? What do we call that thing that measures how much the velocity is changing? So let's say something is speeding up or slowing down. What do we call that? Do we know? Yeah, it's on the title of that page, right? Leilani's like, I think it's right there. It's acceleration. And so if I find the rate of change of the rate of change, or I find out how much the velocity is changed by, taking the second derivative, then I've actually found the acceleration. So I could say, you know, the velocity is changing by 1. So notice on this one, I could have said how, you know, on, let's call this 1, let's call this 2, just so I have something to refer to. On number 2, I could have said, you know, the distance was changing by 3. On number 3, I could say the velocity is changing by 1, or I could just say the acceleration. Anybody remember the unit of measurement for acceleration? It's meters per second. We just call that meters per second squared. Y'all done that in physics? I don't know. You both give me the shoulder shrug. Did you take physics this year? Did you talk about acceleration at all? Don't know? Okay, well, you're covering it now. Look at us go. Physics and math intersecting into one beautiful being. And so this is what I want us to be able to do today, is be able to take these things and interpret them. So I'm going to go on to the next page real quick. It looks like September and Leilani are both good. And what we're going to do is we're just going to stamp this one more time and before we get into an example. So something that you need to know today is that S of t for any of these types of problems are usually talking about our distance. Great. And if I take the derivative of that, I'm going to put this down off to the side. If I take the derivative of S of t, we can mark that as S prime of t. But what did I call the derivative of S of t? What word did I use instead? Velocity. So we could call this instead v of t. So if you see S prime or v of t, that both of those things are talking about something's velocity, right? Because derivative tells us rate of change. I'm going to put that ROC over here. So the rate of change, a change in distance over time. Now, if I take the derivative again, that's where the second derivative comes from. That's just the derivative of the derivative, so I could call this S double prime. Let's say you're not given S to start, right? Or let's say you are given S. You could take the derivative twice. What if you're given velocity? How could you go from velocity straight to acceleration? Well, you would just take that derivative once. So the derivative of distance twice or the derivative of velocity just once is equal to the acceleration. So that's the rate of change is rate of change. How much the velocity is changing by, we call that acceleration. For acceleration, I would prefer, obviously use this. For velocity, I would prefer this, but I need you to know kind of where that comes from. It comes from the first derivative for velocity. It comes from the second derivative for acceleration. Oh man, pen walked away again. Classic. A particle's position along a line is modeled by this function. S of t equals 2t squared minus 16t plus 15. S is measured in meters. That's our distance or position. And t is measured in seconds. That's our time. We're only using positive time values. We're not going back in time. We're going to do two things. We're going to find the position of the particle at t equals 1, and then we're going to find the velocity of the ball at t equals 2. I would. The reason why I would write the whole problem down is because eventually when you get a problem like this, you can go back and find something that looks very similar. Now, if you take it on your phone, you're never going to go back and write it. Well, you got to write it down to submit it for your notes. Oh, everything that I'm doing in here is notes today. September is on something today. She just came in. She came in. God bless the rest of her teachers today.
That is exactly y'all was talking about me in that meeting.
I wasn't even there. I wasn't even there.
No, that's what I knew.
I wasn't even there. What are you talking about?
No, y'all was talking about me in that
Man, I don't know what you're talking about. I honestly have no idea what you're talking about, but this is all very funny to me.
See, you like to play that role, like you didn't know what purpose versus someone else.
Do you think I like hiding information?
Well,
Do you think that like makes me look at this is what I'm talking about. This is why I said God bless your teachers the rest of the today. This is why I said it. Look at you. You're just digging in on everything.
question everybody, you like to play the victim.
She's flipping it on me. She's trying to flip it on me today. I'm not letting it happen. All right. The first part is going to be pretty easy. Is this Sean? Position is pretty easy. I'm just going to use S of t. Let's annotate it. And so we're going to put S of 1 in there. Tell Sean he should be writing this problem down, not he's trying to find his pen. And so all we got to do, since we're given the position function, is just plug it in to find the position. Do your exponents first, right? 2 times 1 minus 16 plus 15. Then we'll do some multiplication. I'll save you some work. Your answer here would be 1. What's our unit? It's the position. That would be our distance. It's not a rate, just the distance, 1 meter. Easy, right? Sometimes it's just a matter of plugging things in, but here's what I saw, and I continue to see. I saw it last year, and I saw it earlier when I taught the seniors this subject, is when I talk about velocity, people took that 2 and they just plugged it into the same equation. They didn't make that jump to realize that velocity is a rate of change of S of t. So I've got to find S prime of t in order to find my velocity. So no, we're not just plugging 2 in here. We got to find our velocity first. So let's find S prime. Y'all know how to find the derivative. Bring the 2 down. Subtract 1 from the exponent. 16t just turns into 16. 15 turns into 0. So now I have my velocity formula. I'm going to write that as v of t. Or v of 2. You can write that as S prime of 2 if you'd like. And what we get here is 8 minus 16, which is negative 8. Now, our units obviously change because velocity is a rate of change. So what is my unit of measurement going to be? Negative 8 what? What per what? Meters per second. And with meters per second, with speed or velocity, we can usually just put m over s there. Done. So yeah, it's kind of just plugging in, but what you've got to do is you've got to understand that velocity is rate of change. That tells me to take the derivative of my position function. I wasn't given velocity, was I? No, I was given this. So just understanding what we have and what we need and how we can get what we need if we need to. All right, y'all. I'm going to move on to this next one in a moment's time. Looks like Leilani and September, you're both done, but I'll check in with anybody at home. And anybody need me to hang out here for 30 more seconds? Sean Jones better not say me. He said yes. All right, I'm going on to the next problem then. You do not need to rewrite the prompt, all right, September? Because it's the same prompt for this one. But this one just has 2 new questions. Okay, so this is the same situation up top, right? This is the same thing. So you don't have to rewrite that, but you do need to rewrite these 2 down here. We'll call this C and D. Now we're going to find the acceleration at t equals 6. And we're going to find all times when the particle is at rest. As you're writing down this part, part C, finding the acceleration, Should be thinking, what's my annotation here? What does acceleration tell me to do? It's either going to be S double prime or V prime, right? So I can either take the second derivative of S, or I can take a derivative of V prime. So let's just remember we had, okay, S prime, we just did that one, didn't we? Wasn't that 4t minus 16? So acceleration is going to be S double prime, which is going to be what? What's 4t turn into? Well, yeah, that's going to be A of t, of course. Yes. But I'm marking to myself, like, how do I find that A of t? It's either S double prime or V prime. So, all right, Stern, what's the derivative of 4t? The derivative of 4t. You're doing too much.
Do I substitute the T for 6?
4.
You said yeah?
No, you're listening to music too much over there.
No, I'm not.
I'm just taking the derivative. I'm not plugging anything in yet. Right, because this is S like single prime, right? This was our first derivative, right? This was V of t. From the last problem, I got to take the second derivative. So I just took the derivative of that. So A of t is just equal to 4. So that tells me 4, and then I'm going to include my label here, meters per second squared. So that tells me what our velocity is doing, if it's speeding up or slowing down. What's up? Because normally, that's a great question. I kind of glanced over that. I would normally plug that in. Where would I plug that into my acceleration formula, though? Is there anywhere to plug that in? For where? Well, I would plug it in for the t, but there is no t anymore because the t went away when I took the derivative. All right, so I don't want to plug it in until I've taken the derivative. Sometimes though, September, I'll take the derivative and obviously there will still be a t there, right, in that last problem, and I could plug it in. No, it's basically saying, like, basically for anything that I were to plug in, t equals 6, t equals 8, t equals 100, our acceleration is always going to be 4 in this instance. All right, lastly, particle at rest. What's my annotation going to be there, Leilani? Velocity equals 0. Yeah, Sean, tell her. Okay, so now, if our velocity is 0, don't we already have that from the last problem? 4t minus 16, right? Wasn't that our velocity formula? So let's just solve it. Add 16, divide by 4, and we get t equals 4.